Hi, my name is Angela Taylor. I'm an electrical engineer turned educator, and I want to share with you a new way I've discovered to teach electronics to young students. This new method is based on constructivism, something you may or may not have heard of before. So let's talk about it. What is constructivism? Well, the name gives you a bit of a clue. It's a teaching method based on the idea that children learn not through rote memorization or absorbing facts from the lectures of teachers, but by actively engaging with the content and constructing the meaning in their minds. Constructivist teaching has a solid grounding in scientific development and application, being championed by developmental psychologist Jean Piaget. If you haven't heard of Piaget, you should look him up. He was a remarkable man who dedicated his life to studying how children learn. Through countless experiments, he and others sat with children of all ages, asking questions similar to those on an IQ test, to understand their logical reasoning and to look for patterns of development. What he discovered was a general path that all of us walk, stage by stage, as we work to understand our world. Piaget's theory of cognitive development contains 4 stages, beginning with the sensorimotor stage. Because learning starts at birth, in this stage, infants learn everything they can about the world around them by interacting with objects, touching things, and usually putting them in their mouths. Babies don't know much yet, and explore their world through physical interaction, tactile, and sense experience. They can't even retain images in their memories yet, which is why peekaboo is so exciting for a baby. When you cover up your face, it really is as if you've disappeared. This stage usually lasts about 2 years, though of course every child is unique and may take a slightly different amount of time to learn. All those tactile experiments with physical manipulatives eventually leads a toddler to the next stage, the preoperational stage, where a child is beginning to form mental images of the world around him. This is truly the beginning of abstraction, of symbolic form, which can be seen in the drawings of a young child. The figures of mommy and daddy are not literal, with proper proportions and realistic shading, but rather simple stick figure symbols of people and objects. A child in this stage will begin to notice attributes and qualities of an object without understanding how they are related. For example, a 5-year-old girl may say, "The sun is big because it is yellow," a statement which observes 2 attributes of the sun, but fails to effectively correlate them. This stage continues until around the age of 7, at which point the concrete operational stage is entered. The concrete operational stage is the real beginning of logical thought, if A, then B. But in its infancy here, it is very rigid and local. Like, I noticed that this ball that's filled with air and made of rubber bounces, but I'm not sure that that one does. Or similarly, I can see that 20 marbles fill this jar and 40 fill the jar that's twice as big, but I have no idea how many will fill the jar that size is right between the 2 other jars. This stage is filled with situational facts that don't yet create a flowing image of universal rules, and as such, there is still a strong emphasis on using physical manipulatives to compute quantities such as 5 plus 4. It makes much more sense at this stage to add 5 marbles to 4 marbles than to contemplate the more abstract addition of just 5 plus 4. A child in this stage may ask, 5 what? Plus 4 what? This stage lasts till about 11 years old. Then finally, the last stage is entered, formal operational. This is the stage at which full logical ability is able to form, when the abstract concepts of 5 plus 4 can be retained and computed, devoid of any physical manipulatives or situations to relate to. This is the point at which pure mathematical equations can be truly understood, related in the brains of children to physical examples conjured when necessary, like, I can think of 5 plus 4 as 5 apples plus 4 oranges to equal 9 fruit, or $5 plus $4. Either way, the sum is 9. This stage of abstract, universal logic lasts throughout life, though sadly some people do not ever arrive here due to poor teaching and mentoring through the previous stages, but that's a talk for a different day. Let's look at these 4 stages through an example in mathematics. Multiplication. Starting at the beginning in the sensorimotor stage, let's slowly build up our logic. So you'll have to imagine that your intelligence is equivalent to a child at each age and stage. Now, let's say you have a bunch of marbles or shiny gemstones, and you want to count them to see how many you've collected. What are different strategies you can come up with to count? The first, of course, is one at a time. That one always does the trick, but suppose you have a lot of shiny gemstones and want to count faster. How about counting by twos or threes? In this stage, we practice the beginning of number sense, seeing patterns and counting objects. Now, let's move to the next stage, where we begin to realize that instead of just counting randomly assorted piles of stones, we can form them in an organized pattern, like using them to form the shape of a box, or array if you want the more mathematical term. What can we notice about the stones in our box? Well, in this picture, I can see that there are 5 rows and 5 columns in my box, and altogether there are 25 stones that make up the shape of it. Eventually, I can learn to see that I can add up the amount of stones in one row by counting by 5s. 5 plus 5 plus 5 plus 5 plus 5. And now that we have a neat box shape to look at, we can apply it to lots of different dimensions, and in that way visualize different counting patterns. I want you to visualize a box that has 10 rows of 2 stones each. Can you find out how many stones make up that whole box? Then, it's fun to apply this array idea to tasty things like food, since that involves our interaction with the food because we get to count and then eat the cookies. Here we also start to think of the numbers of rows and columns that make up the box as the dimensions of the box, and the total amount of cookies or chocolates it contains as the area of the box. This is an important geometrical idea that helps us tie together those mathematical concepts with physical objects we encounter in our daily lives. Eventually, we can visualize the array of objects in our mind's eye and make a sketch of them on paper. In this case, the objects are stars. We can also start to write down our observations and mathematical equations. If we multiply the dimensions of the array, we get its area. A mathematical equation for multiplication can be written as one dimension times another equals the area. Hey, this is the fastest way to count objects that we've found yet. Remember, we started this whole exercise to find a way to count shiny pebbles, real physical objects. We always keep in mind that our mathematical symbols and equations represent those original physical objects. Eventually, we can hold those physical objects in our mind's eye so well that we don't need to work with them in our hands and can focus more on the equations and abstract representations of them we can write on paper. At this point, we can just draw a symbol of a box, recording its dimensions on the sides of the box, and by all the work of studying physical arrays, their dimensions and areas, we can come to know the areas of hypothetical boxes. And we can extend this to breaking up objects and numbers into smaller pieces to solve. In this example in the upper right, 7 times 32 is computed by creating a box with one dimension of 7 and the other of 32. But notice that the dimension of 32 is split up into a compartment of 30 and one of 2. This makes the mental calculation easier, for we might not know what 7 times 32 is, but we can figure out what 7 times 30 is, and what 7 times 2 is, and add those together. Eventually, as you see on the bottom left, we can move away from this box method altogether and just use the symbolic form, remembering the whole time that what those numbers represent physically. Having the box method to start with enormously helps students understand place value and why, when multiplying 89 by 7, that means 80 times 7 plus 9 times 7, not 8 times 7 plus 9 times 7. Okay, so that's a brief overview of constructivism as it applies to teaching and learning math. So how can we extend this to electronics? And why would we want to? Well, in my own experience of learning and teaching electronics, I've found that this is perceived as a very difficult subject to learn. Indeed, if you tell someone you're studying electromagnetic field theory, they'll look at you with awe and respect, as many regard the subject matter incredibly complex. As it turns out, it's not so much the subject matter that's complex, but more so that the method of teaching has classically failed to take into account the stages of cognitive development, especially the fact that most of our learning comes through visualization and interaction. And electricity is really hard to see, except in natural phenomena like lightning, or when something like a transformer blows and catches fire. But when creating a simple circuit, you simply can't see the electricity flowing. So when something goes wrong, it's much harder to figure out what happened. as compared to figuring out why your bike stopped working when a rock got caught in the chain. So I've decided to take this constructivist model, which works so well in teaching math, and apply it to teaching electronics. And similarly to Piaget's 4 stages, I've created my own 4 stages of exploration that I think could be applied to other science and technology education. In the first stage, we start with what seems obvious to us, what we experience every day in our physical environment. We begin with a question about such a phenomenon and ask about each student's personal experience with it. In the second stage, we begin by forming a hypothesis about how phenomena we experience are interrelated, like why a leaf blows in the wind. And then we develop an experiment to test our hypothesis. For many of my younger students, this is the first time they've been introduced to the scientific method, so we spend a great deal of time discussing and exploring what makes an experiment useful and reproducible, and talk about controlling the variables to only have one thing changing at a time. After we perform our experiment, we move on to the next stage, which is analyzing our data. What happened in the experiment? Was your hypothesis correct or incorrect? Perhaps when analyzing the data, we realize we need to perform more experiments to really get a hold on the situation and phenomenon being observed. Eventually in this stage, we work toward creating rules that seem to fit what we observed in the experiments. If possible, we'll put these rules in the form of an equation. After we believe that we've created a mathematical equation that sums up what we observed in our experiments, we'll apply that equation to our breadboard or piece of technology, which should work if our equation is right. Here we'll verify our equation through the working or non-working of our applied technology. If our piece of electronics works, we figured out a law or rule of science. If not, we go back to the previous steps and try again. Okay, so that's the general breakdown. Let's see how it applies more specifically to constructivist electronics. For teaching electronics, many have found it useful to start with the analogy of the motions of water. Think about your experiences with natural bodies of water, rivers, lakes, waterfalls. What makes the water move? Why do the waters in rivers move so rapidly but those in lakes don't? So we start here by relating to our physical experiences with the motions of water and consider any properties we might think apply and explain why and when water flows. If we notice properties or remember experiences, we can think about how they might relate to the concepts of voltage, current, and resistance. What do you think those words mean? You may have heard the word current as it relates to the flow of a river. Do you think it might be similar in an electric circuit? Notice that we aren't starting with definitions or terms to memorize, just questions to ponder. Once we've had time to really think about our experiences with water and come up with our own hypotheses on how those 3 terms, voltage, current, and resistance, could be related to water, we try to guess how the terms might be related to each other. So think. In a river, if there's a lot of resistance, say in the form of branches or rocks, does that seem to increase or decrease the current? What about the voltage? When we formed our own hypotheses, we write up an experiment to perform, to verify or modify our hypotheses. In my classroom, I have a water circuit to really tie together the physical experience of water with the metaphor of electricity. And with it, we can see the water flowing and how resistors affect the current in the circuit.
That song scares me. Everything scares you. And that's a series parallel combo. Series parallel. Very water. Look at what I drew. I'm serious. It's not good. It's a water circuit. It's water going through pipes. How did you make it do it? Levi, do you want me to stay and help you clean that up? Yes, please. There's my
Okay, after performing one or several experiments with a water circuit, we've noticed that when the resistance in a circuit increases, the current decreases. We also noticed that when the voltage increases, the current increases. How can we summarize this into a mathematical rule with variables assigned to each quality? Well, what students eventually create is Ohm's Law, the first theory of electronics, that is, that voltage is proportional to the current times the resistance. Before moving any further, we fully contemplate this equation, checking that it truly represents each phenomenon we observed in our experiment. It's not just some abstract equation to remember, but a simple combination of symbols to represent what we observe and understand to be true. After we discover Ohm's Law, or some other version we believe could be true, we test it by creating a breadboard circuit with a battery, wires, and a light, and measure the values of voltage, current, and resistance with a multimeter. We do this a number of times. We do this with a number of circuits, so we have a plethora of data to go through and plug into the equation we created to see if the data fits. If not, we go back to the water circuit and try again to find an equation that works. When we do finally truly create Ohm's Law and it works in our circuit, we feel amazing. Electronics is now not just a mysterious magical byproduct of an equation someone else gave us, but something we created and truly, deeply understand. I want to note here that what I've discovered through teaching is that it's most effective to combine the teaching of science with the application of such knowledge, the technology that comes from the theory. If you're just in physics class memorizing Newton's laws and computing vectors and momentum, it may stay in your brain as only a mental exercise. But when you discover Newton's laws, then apply them to create something from your own imagination and conception, the concepts being studied come alive and become part of the way you experience the world around you. Science isn't meant to be just a bunch of memorized facts, but a way of interacting with the world. Now, to break it down even farther, I've found through teaching electronics that the water analogy only goes so far. Then it has to be replaced by other concepts. In fact, I've found that there are essentially what I'll call 3 tiers of concepts which are useful for understanding electromagnetism. The first, of course, is the water analogy, which works quite effectively for considering those 3 primary qualities of electricity: current, voltage, and resistance. It also helps us understand intuitively what happens when we have components in series, in parallel, or in some combination of both. This is actually quite a lot to begin with, and solidly lays the foundation of understanding the general flow of electricity through a circuit. In fact, it's all you really need to consider for something as simple as wiring the lighting in a house. But after we've exhausted the water analogy and want to get into slightly more complex components, such as capacitors, we need to move from considering electricity as a fluid and think of it as an enormous collection of individual electrons. So at this tier, we do the 4 stages of scientific investigation all over again, but this time prefacing it with some basic introduction to atoms, the periodic table, and the simplest attractions between atoms and electrons. So there is some giving of information here that cannot be just experienced and intuited. However, we keep it as minimal as possible. Once we understand that there are such things as tiny, microscopically small particles called atoms that make up everything, and that itself is something to spend some time to let sink in, we conduct some basic experiments to see just how those electrons interact with one another and with positively charged atoms. I will tell you that from some simple experiments with rubbing balloons on our heads, on walls, and testing how closely statically charged balloons need to be to attract each other, my students were able to intuit and create Coulomb's law, which states that the amount of attraction between 2 charged objects, like balloons, is proportional to the charges of each balloon individually and inversely proportional to the square of the distance between them. That is to say, the more charge the balloons have, and the closer they are, the more likely they are to attract one another. By extension here, we consider objects which attract and repel, and consider how a bunch of electrons would interact if they were spread evenly over one of 2 adjacent plates, which is what happens inside a capacitor. Because like charges repel, and because of the newly discovered quantization of charge, we understand that eventually one plate will fill up with electrons, and if the other adjacent plate doesn't have any electrons on it, the two plates will be, in a way, attracted to each other. And the difference between the charged electrons on one plate versus the other is, in a way, the definition of the voltage between them. The interesting thing here is when we put a capacitor with said properties into a circuit on a breadboard with a light bulb. At first, the light glows brightly, and the electrons are flowing through the circuit and filling up one of the plates of the capacitor. But eventually, when the plate gets full, no more charge flows through the circuit, and the light bulb grows dim until it turns off completely. This second tier is an order of magnitude more complex than the circuits created before, because now we have qualities of electricity varying in time. Whereas before, with just a resistor and light bulb, when you turn the circuit on, the light glows, and when you turn the circuit off, the light goes out. Now, the light gradually turns on or off, even if you don't physically touch the circuit after you turn it on. After we've thoroughly studied everything we can about nonlinear voltage, current, and resistance, and how it applies to the workings of capacitors and transistors, and by application of transistors, many varying integrated circuits and chips, we move on finally to the third tier, magnetism. Again, working with the 4 stages of development and investigation, we begin by studying magnets and their attraction and repulsion to each other. We notice similar properties of magnets as we observe between point charges, and eventually we explore how magnetic fields are induced in current-carrying wires, and vice versa. Whereas, while studying electric fields, we were looking at a plane of charges in a capacitive plate, while studying electromagnetism, we are looking at a 3-dimensional cross-section of charge around a wire or magnet. And we notice induced magnetic or electric phenomena by something moving through time and space. A magnet repeatedly moved in and out of a coil of wire will cause a current, whereas a magnet simply placed and left in a coil will not create a lasting current. This represents another order of magnitude and complexity over simple electrostatic fields, or even the now comparatively basic water metaphors we looked at previously. Once we understand magnetism and the relationship between electricity and magnetism, we open our electronics toolbox to coils, relays, solenoids, transformers, and eventually motors and generators. We can now explore all the nuances of transient effects between wires used in transmission lines, or resonance between components in a circuit, and other seeming anomalies that we couldn't have previously understood or accounted for. We have now encompassed all of electromagnetism and electronics possible in classical study. Now, there's just one more level of complexity I want to add here that I've noticed in creating and studying all of this, and it is the overlaying of gradual progression in complexity for the science concepts, the technological electronic components, and the mathematical concepts needed to explain and understand what's going on. So let's look at that briefly, then we're done. To recap what we've already seen and note the pattern that may or may not have been apparent all along, when looking solely at the complexity of scientific concepts being studied, we see that we start with a water analogy, then move on to static electric fields, and end with dynamic electromagnetic fields, each of which is an order of magnitude more complex than the one before it. When we look at the progression of electronics components available to use in creating actual circuits, we start with basic components like resistors and light bulbs, then move to capacitors and semiconductors, then open finally to include electromagnetic components. Again, this denotes a progression in orders of complexity. Finally, when we consider the mathematical reasoning and relationships emergent from the study of each of the 3 stages, we see that, just in terms of dimension, we start with a 1D, or a line connecting 2 points, which is a simple circuit, then go to a 2D, a plane, which is the plates of a capacitor, and then go to 3D or even 4D, like the volume of a box, which is the changing magnetic field encircling a current-carrying wire. Additionally, you'll see, in terms of voltage and current relationships, that we start out with a linear relationship, move to a nonlinear growth or decay curve, and eventually end at an oscillating sinusoid of varying current and voltage. I mention all this because I personally believe that it is incredibly important to introduce each concept in the study of electronics in its proper place, holding in mind the relative complexity of the topic you're introducing. So don't try to jump right into transformers' electromagnetic induction right off the bat. Don't jump from semiconductors to inductors without fully appreciating the accompanying jump in conceptual complexity. I've seen that happen before in other instructors' teaching methods, and I strongly disagree. And now you can see why. So, that's it. My concise overview of how and why to teach electronics in a constructivist method. While some of the particular content may have been over your head, I hope what you take home is the relative simplicity of understanding these seemingly complex concepts when you study them in a gradual, logical order. Electronics doesn't have to be confusing or overwhelming. It can be amazingly logical and intuitive if it's approached the right way. And it should be fun! Thank you for watching.